we discussed Lagrange's mean value theorem yesterday and also saw some of the consequences, and towards the end I said that we shall be discussing one more mean value theorem, and namely Cauchy's mean value theorem. So let us see the statement of that. Cauchy's mean value theorem. Okay, and I shall use the standard short form for mean value theorem. Main difference is in case of Lagrange's mean value theorem you deal with only one function, whereas in Cauchy's mean value theorem you deal with two functions. Okay. So we shall begin with two functions. Suppose f and g, these are two functions from AB to R, are continuous. Again the assumptions are similar, continuous in this closed interval AB and differentiable in open interval AB. Okay. Then there exists a number C in AB such that FB minus FA divided by GB minus GA, that is equal to F prime C divided by G prime C. This is how it is given in most of the books, right? But you can see that in this formulation there is a slight problem here. Okay. What is the problem? What if this GB is equal to GA? Okay. What this, and similarly what will happen if this G prime C is equal to 0? Okay. So in order to avoid that difficulty, one can, there are two ways of avoiding it. One can right in the beginning assume that G prime x is not 0 anywhere in AB. If G prime x is not 0, is it clear that this GB minus GA also cannot be 0? Right? That follows from Rolle's theorem. Okay. Because if GB were equal to GA, then at some point see G prime x would become 0. So okay. But another way to deal with that is we can just avoid this division. Okay. I can write this same formula in a slightly different form. Okay. I can write this as, so instead of writing it like this, I shall write it like this: FB minus FA into this G prime C, that is equal to GB minus GA into F prime C. Okay. If I write it like this, then there is no division involved and we don't need to make any extra assumptions, right? So we shall write it in this form. Okay. Right. So now we don't have to say anything about G prime x not equal to 0, etc. Okay. Okay. Now before proceeding further with the proof, okay, let us make one or two observations. Is it clear to everybody that Lagrange's mean value theorem is a special case of Cauchy's mean value theorem? Okay, right? That is, if we take Gx is equal to x, okay, if we take Gx equal to x, you will get this Cauchy's, you will get Lagrange's mean value theorem. Okay, right. Because Gx equal to x, then G prime will be 1, so this will be 1 and that will be F prime C, this will be just B minus A. Okay, alright. One more thing, it is quite tempting to attempt the proof of Cauchy's mean value theorem by using Lagrange's mean value theorem. Okay. For example, one might say that apply Lagrange's mean value theorem to both the functions. Okay, so using that you will get FB minus FA is equal to F prime C into B minus A, and similarly GB minus GA is equal to G prime C into B minus A, and then just substitute here, okay, then just substitute here, okay. But is this correct? What is wrong with this? Right, that is when you are applying Lagrange's mean value theorem to two different functions, the point C that you may get will be in general different, okay. That C, so this C and this C need not be same, okay. So correctly, this there will be some C1 here, then there will be some C2 here, and then you will not get this conclusion. So Cauchy's mean value theorem has to be approached in a different manner. But once that is clear, what we will do is that we shall basically imitate the proof of Lagrange's mean value theorem to prove Cauchy's mean value theorem, okay. Though we do not use Lagrange's mean value theorem, but we use the ideas in the proof, okay. And what was the idea? We constructed some auxiliary function big F, okay, and showed that that function satisfied all the properties of all the hypotheses of Rolle's theorem, and using Rolle's theorem we got it out. So okay, so we do the same thing here, okay. So define auxiliary function F, define F from AB to R by big F at X is equal to, in fact this expression gives us an idea of what that function big F should be, okay. We shall define it as follows. So FB minus FA multiplied by Gx minus GB minus GA multiplied by Fx. Okay, and suppose we show that this function satisfy all the hypotheses of Rolle's theorem, then by Rolle's theorem we will say that there exists some C such that this big F prime at C is equal to 0. Okay. Is it clear that that will immediately give this, because big F prime at C is nothing but FB minus FA into G prime C minus GB minus GA into F prime C, okay. So the only thing left now is to show that this big F satisfies all the hypotheses of Rolle's theorem. What are those? This big F must be continuous in AB. Now what does continuity depend on? FB minus FA is anyway constant. So this G is, so wherever G is continuous, big F should be continuous. Similarly, wherever small f is continuous, big F also should be continuous, and we are given that small g and small f are continuous in the closed interval AB, okay. So we can observe that big F is continuous next is differentiability, again the same argument, because wherever small f, because only see this big F is some kind of a combination of small f and small g, okay. All other things coming into picture are just constants. So wherever small f and small g are differentiable, big F will also be differentiable, right, and that is the case in the open interval AB, that is small f and small g are differentiable in the open interval AB. So big F is also differentiable in open interval AB, okay. So what's that? Big F is differentiable in open interval AB. So the final step is hence by Rolle's theorem, we can say that hence by Rolle's theorem. Oh right, we again this is something I have forgotten yesterday also, okay. So we need to check the values of F at A and B, right, okay. So what is big F at A? Okay, so it is FB minus FA into GA minus GB minus GA into F of A. So what is that, this Fa into Ga will cancel with this Ga into Fa, right. So what will remain is Fb Ga minus Gb Fa, okay. Similarly look at big F at B. So big F at B again, that is Fb minus Fa into Gb minus Gb minus Ga into Fb. So this time what happens, this Fb Gb will cancel with this Gb Fb, okay. So what remains, minus Fa Gb from here, minus Fa Gb from here, and minus this becomes plus Ga Fb from there. Okay, so is it same as this? Okay, so what we have is Fb is equal to Fa, that is big F at B is same as big F at A, okay. So we have verified that assumption also, okay, right. So we can say that by Rolle's theorem there exists C in the open interval AB such that big F prime at C is equal to 0. Okay, fine, you can say by Lagrange. But see, when we discussed Rolle's theorem, that time itself we also made a comment that Fa equal to Fb equal to 0 is not very crucial, okay. See, for example, suppose Fa equal to Fb were some other value, suppose Fa equal to Fb is equal to k, then you can consider a function f minus k, right, and then that will be 0 at both the endpoints, right. So all that really matters is that the values at A and B are the same, okay. There is some convenience in taking them to be 0, but that is really not very crucial, okay? Because adding and subtracting constants does not change the values of the derivatives, right. Instead of the function f, you can take the function f minus k, and the derivative of f minus k will be same as the derivative of f, right. Okay, so you can, but it is okay, I mean instead of Rolle's theorem, if you want you can say Lagrange's mean value theorem, that does not matter, okay. Alright, so what remains now, what is this f prime of C? So look at this, so at any point big F prime at x is nothing but this into G prime x minus this constant into f prime x. So in particular at the point C, this will be same as Fb minus Fa into G prime C minus Gb minus Ga into f prime C. Okay, and saying that this is equal to 0, it is same as this equation here, okay. That is the proof of Cauchy's mean value theorem. Then before going to the other problem which I mentioned yesterday, namely about the types of continuities of the derivatives, let me also discuss one more very frequent application of this Cauchy's mean value theorem, especially in the undergraduate calculus, okay. You would have come across what is called indeterminate forms, okay, and forms like 0 by 0 or infinity by infinity, etc., etc., okay. What are the issues involved there? That is, suppose you have functions like this, let us say you have functions like fx and gx, okay. and suppose you want to look at limit of this as x tends to a, okay. And suppose it so happens that fx also goes to 0 as x tends to a and gx also goes to 0 as x tends to a, okay. Then what can we say about fx by gx? Okay. See, usually this depends on, even though both these functions go to the same, go to 0, whether the limit of fx by gx exists or not depends on which goes to 0 faster, okay, right. For example, x also goes to 0 as x goes to 0, x square also goes to 0, but whether the limit will exist x by x square or x square by x, that depends on which one goes to 0 faster, okay. So in order to discuss that, one might want to discuss the rate of convergence and things like that, but we will not get into that, okay. These things are decided basically by the derivatives, okay, how fast a function goes to 0. So instead of, so what is done in this so called indeterminate form is that you look at this f prime x by g prime x, f prime x by g prime x, and suppose the limit of this exists as a finite real number, then the limit of this also exists, then the limit of this also exists, and that limit is same as whatever is the limit of this, okay. Suppose this limit is limit as x tends to a is equal to L, then this limit also exists and that is also same as L, okay. This is something you may have used quite often, okay, but without perhaps realizing that this really depends on Cauchy's mean value theorem. So let us just say a few things about that connection and then I will come back to the other problem, okay. So this is the, okay, this is usually called L'Hopital's rule. Okay. We will write this as a theorem, okay. Okay. Of course, since now we are looking at the point limit at the point A, we will prefer that A is not the end point of the interval, okay. So let us say that let us say suppose f and g are differentiable in some interval I containing A. Actually, as you know, strictly speaking, when we talk of limits, the function need not be defined at that point A, still we can talk of limit of fx as x goes to A. So one could have said that it is differentiable in some interval I containing A, except perhaps at the point I, okay. But we will not go into that kind of finer points right now, okay. Those refinements one can make later. Now my objective simply is this, to illustrate that Cauchy's mean value theorem is crucially involved in this rule. Suppose further that limit of fx as x tends to A is 0 and limit of gx as x tends to A is also 0, okay. This is the so called indeterminate form 0 by 0, okay. This is that is how it is usually described, okay? Indeterminate form 0 by 0, okay? And limit of f prime x divided by g prime x as x tends to A is equal to L. Then the conclusion is that limit of fx by gx also exists, okay, and that limit is same as L, okay. Then limit of fx by gx as x tends to A is equal to L, okay. remember this symbol means all the things that the limit exists and its value is L. Okay. Now let us see how one proves this and where exactly this Cauchy's mean value theorem comes into picture. Of course we have to assume here one more extra thing. Okay. Here we avoided assuming that G prime x equal to 0 by rewriting the theorem in this form, okay, but there we need to discuss this ratio f prime x by G prime x. So here we cannot avoid assuming that G prime x is not equal to 0 in I. Okay. So there is one more assumption here, f g are differentiable in the subinterval I containing A and G prime x is not 0 for all x in I. Okay. Let us first see what is the meaning of this statement. Let us use our usual epsilon delta definition. Okay. What is the meaning of saying that limit of f prime x by G prime x equal to L? It is that given epsilon bigger than 0, there exists delta bigger than 0, that something happens for those epsilon and delta. Okay. What is that something that we shall write precisely? Okay. So let us just rewrite that statement. Let us say that let epsilon bigger than 0 is given. Let epsilon bigger than 0, then there exists delta bigger than 0 such that whenever mod x minus a is less than delta, okay, the difference between this should be less than epsilon. Okay. Difference between this should be less than epsilon, that is if mod x minus a is less than delta, then mod f prime x by G prime x minus L is less than epsilon. Okay. Only thing is now I will make a slight change in the notation here. Instead of using this letter x, I will change it to C, because I want to use the mean value theorem and use the property of the C. Okay. So I will say that if mod C minus a is less than delta, then mod f prime C divided by G prime C minus L, that is less than epsilon. Okay. Now let us rewrite this statement. Okay. Saying that mod C minus a is less than delta, it's same as saying that C belongs to a minus delta to a plus delta. Okay. C belongs to a minus delta to a plus delta. Okay. And similarly this means, that is if, that is we can say that is if C belongs to a minus delta to a plus delta, then this f prime C by G prime C lies between L minus epsilon to L plus epsilon. Okay. Then L minus epsilon less than f prime C by G prime C, this is less than L plus epsilon. Okay. And this should happen for all C in a minus delta to a plus delta. Okay. Now let us consider some points x and y in this interval a minus delta to a plus delta. Okay. Consider x y such that, okay, for the time being let me say a less than y less than x less than a plus delta. Okay. A less than y less than x less than a plus delta. Okay. And look at this ratio fx minus fy divided by gx minus gy. Okay. All right. Now we can say that fx minus fy divided by gx minus gy, for this, since f and g satisfy, f and g are differentiable in the interval I containing a, So in particular those are differentiable even in this interval y to x, okay, in this interval y to x. So we can say that by Cauchy's mean value theorem there exists some c lying between y and x, there exists some c lying between y and x such that this is same as f prime c by g prime c, okay. So this is, that is, you can say that this is equal to f prime c by g prime c, okay, for some c in the interval, okay, for the time being let me simply say the interval y to x, okay, interval y to x, and this is by Cauchy's mean value theorem, right. Okay, right, okay. Now does this interval y to x contained in this, is this interval y to x, okay, this is a y, interval y to x is because a is less than y, remember if you just draw the diagram here, suppose this is a, let us say this is a minus delta, this is a plus delta, we have taken, okay, how did we take this, we have taken y here and x bigger than that. So this interval y to x is a part of this interval a minus delta to a plus delta, and what we have said is that for every c in this interval f prime c by g prime c should be less than L plus epsilon and bigger than L minus. So it applies in particular for this c also, okay, it applies in particular for this c also. So we can say that this is less than L plus epsilon and bigger than L minus epsilon, okay, okay, okay. We shall just take this inequality further, okay, and then see what happens. Okay. Okay, so what we have here, L minus epsilon less than fx minus fy divided by gx minus gy, this is less than L plus epsilon, okay. And this is true for which y and which x, it is true for any y and x which satisfy this, okay, right. So what I would now say is that you fix this x and let this y approach a, okay, because this inequality is true for all y, this inequality is true for all y. So we can say that fix x and let y tend to a, okay. If y tends to a, what will happen to fy? Look at what we have assumed here, okay, okay. We have assumed that limit of f as x tends to a, fx as is 0, okay. So whether you take it x or y, it does not matter here, okay, right. So fy will go to 0 as y tends to a, and similarly gy will go to 0 as y tends to a. So what it will mean is that in the limit fx by gx will lie between L minus epsilon to L plus epsilon, okay. So then what we will say is that then L minus epsilon less than fx by gx less than L plus epsilon, because these two numbers will become 0, okay. These two numbers will become 0, okay. And that's what this says, that is what does this mean, that given epsilon you should be able to find a delta, okay, such that whenever x lies between a minus delta to a plus delta, fx by gx should lie between L minus epsilon to L plus epsilon, that is what we have shown, okay. So this last statement means this, that limit of fx by gx as x tends to a is equal to L, okay. So we have seen here that this L'Hopital's rule in case of this indeterminate 0 by 0 basically uses Cauchy's mean value theorem, alright. Okay. Now I will give you an exercise, if you have followed this proof, okay, then do the same thing for the infinity by infinity form, okay, infinity by infinity form, okay, right, just try to imitate whatever we have done for that. Okay, what is that? There will be only one change here, this will be replaced by infinity, and I believe you know what is meant by saying that limit of fx as x goes to a is infinity, right. Use the definition. What is the definition? That given any positive number m, there exists delta etc., such that fx should be bigger than m for all x in a minus delta to a plus delta. That is the meaning of saying that limit of fx as x tends to a is infinity. Similarly for gx. Okay. So do the same thing what we have done here for 0 by 0 form to infinity by infinity form, okay, and try to do it yourself. Okay. Now let us come to the consideration of the theorem which we have mentioned earlier, namely that we want to show that derivative of a function cannot have jump discontinuity, right. Okay. To do that, let us also observe one more thing. Okay. Or let me remind you one. Yesterday we had defined what is meant by local minimum and local maximum. Okay, and we have said that if f has a local minimum at the point x naught, okay, then and if it is differentiable at that point, then that derivative must be 0, right. Now we can say the same thing in a slightly different language, because that is how we are going to use in this theorem. Suppose we know that the function is differentiable, okay, and at a point x naught, and the derivative is not 0 at that point, okay, can we say that there can be no local maxima or local minima? Okay, let me just write. Okay, this is the observation. Okay, suppose f is differentiable at x naught and f prime at x naught is not 0. Okay, f prime at x naught is not 0, then f does not have a local minimum or maximum at x naught. Okay, it is basically writing the same statement in a different language, right, because if f in fact did have a local minimum, then since it is differentiable, the value of the derivative should be 0. That is not the case, so it cannot have a local minimum. Similarly, it cannot have a local maximum, right. Okay. Then there is one more property that we shall recall. Perhaps you would have heard of this, what is called intermediate value property. This is usually discussed in connection with discussing connectedness. Okay. That is, one can prove that a continuous function defined or image of a connected set under a continuous function is connected, okay. And in the real line only connected sets are intervals, okay. So if you define a real valued function on a connected set, then its image must be an interval, and once you say it is an interval means what? If the function takes any two values, it must take all the values in between those two values, okay. That is precisely what is called intermediate value property, okay. And this property is there for the real valued functions defined on a connected set, but it can be there for other functions also, okay. And derivatives of the functions are one such class, okay. And that is what we will prove now. Okay, so before doing that, let us also write a precise definition of what is meant by saying that intermediate value property. What is the property? What is meant by intermediate value property? That is, okay, let us say, suppose, let us take as well f is defined from AB to R. okay. Now we will say that f is said to have this, okay, I will just write this as IVP, intermediate value property. If suppose you take any 2 points in xy, if for every xy in AB and let us say I will take any point, let us say the point gamma in the interval, okay, now it depends on whether fx is smaller or fy is smaller, okay. Suppose fx is smaller, gamma is in the interval fx to fy, okay. Suppose gamma in fx to fy or gamma in fy to fx, right. That is, what are the possibilities? See, what does this mean? See, what this means is this, that is fx less than gamma less than fy, or okay, let us just explain this, that is, or fy less than gamma less than fx, okay. This is what you mean by saying that take some point lying between fx and fy, okay. If fx is less than fy, this first thing will happen. If fy is less than fx, that will. And so what does this intermediate value property says? That there should exist some point, in the interval going from x to y, again it may be from x to y or y to x depending on whichever is smaller, okay, okay. So for every such point x, y and ab there exists, let us say that point is z in xy or yx depending on whichever is smaller, okay, depending on whichever, such that f of z is equal to this point gamma, f of z is equal to this value gamma. That is, if you take any two values, if you take any value lying between fx and fy, there exists a point z, that point z also lies between x and y, okay, that point z also lies between x and y. In fact it cannot be x or y, so in fact one should write here open intervals, because here you have strict inequality, z cannot be x or z cannot be y, okay, right. So or open interval here also yx, such that f of z is equal to gamma, okay. Alright, so now what do we want to say? That if a function is differentiable, then it has intermediate value property, okay, alright. So that is the theorem. Of course, since we are talking about differentiability, we can just take open interval, okay. Suppose f from AB to R, that is I will take now open interval AB to R is differentiable in this open interval AB. In AB, okay, then f has intermediate value property, sorry not f prime has intermediate value property, okay. F is differentiable in AB means f prime is defined as a function at all these points, okay, and that function f prime has intermediate value property, right. Okay, let me again remind you that how did we start this whole thing? We started with the question whether there exists any function whose derivative is integral part of x, okay, right. And after proving this theorem we can answer in the negative, because no function can have integral part of x as its derivative, because all derivatives must satisfy intermediate value property and the function integral part of x does not satisfy that, okay, right. Okay. Now let us come to the proof. Okay. We will just take one of these cases because here while defining it is okay to consider all such possibilities. We will just assume that x is less than y and fx is less than fy. Okay. So consider a less than x less than y less than b and suppose fx is less than gamma less than fy. Okay. If we show in this particular case, the proofs for all the other cases will be similar, okay, right. X is less than y, fx is less than fy, then we can take similarly one can prove when fy is less than fx or y is less than x and things like that. Okay, all right. Okay. So what we will do is we shall also define a new function which depends on the given function f and use some of these things for that function. So let us say define g from ab to r by g of x. Oh no, we already used that letter x, let us use some other letter here. Okay. G of t as f of t minus lambda times t, let us say f of t minus lambda times t for t belonging to AB. Okay. Now what can we say about G? Okay. First of all, is it clear that G is also differentiable in AB? Okay. Because what is G? F is differentiable and lambda times t is also differentiable, in fact its derivative is lambda. Okay. So we can say that then G is differentiable in AB. AB. Okay. What is G? What is G prime at any point? G prime at t is nothing but f prime at t minus lambda, right? Okay. We can also say that. We can also record it also. G prime at t is equal to f prime at t minus lambda for t in AB. Okay. And so what is G prime at x? G prime at x is f prime at x minus lambda. Oh, I think here it should have been f prime at x, f prime at y. Okay, I am sorry, because we are remember we are trying to show that f prime has the intermediate value property, not f. Okay, so we should have taken f prime x less than gamma less than f prime y, and I think here also I want to take this not lambda but that constant gamma. Okay, so we will make that change. Okay, so G prime of t is f prime t minus gamma, and this is also G prime x is f prime x minus gamma. Okay, all right. So let us come back to the question. G prime x is f prime x minus gamma. So what do we know about this? F prime x is less than gamma. F prime x is less than gamma. So f prime x minus gamma must be less than 0. right, f prime x minus gamma must be less than 0. So g prime x is less than 0. What about g prime y? G prime y is f prime y minus gamma. What about this? Gamma is less than f prime y, so f prime y minus gamma must be bigger than 0, right. So f prime y minus gamma is bigger than 0. Okay. Now our argument is as follows. Okay, you look at this function g in the interval x to y. Okay, look at the function g in the interval x to y. Okay, right. G is differentiable in AB, and hence it is also continuous in AB, and hence continuous in the interval x to y. That is a compact set. Okay, so every continuous function on that compact set must have a minimum. Okay, must have a minimum. Okay, let us just say that. Okay, is clear, since G is continuous, in xy, which is an interval contained in AB. Okay, and okay, this interval is, this set is not compact, but this is. Okay, this set is not compact, but this is. So G, when you look at G defined on this interval, it has a minimum. Okay, it has a minimum. Okay, so one can say that suppose I call that minimum as Z. Okay, there exists Z in xy such that f has, I will simply say f has a local minimum at Z. At Z. Now there is only one question, okay, whether this Z is an interior point of xy or one of the endpoints. Okay, okay. Suppose Z is equal to x. Okay, it will mean that this G has a, oh, I am sorry, not G has a, okay, it will mean that this G has a local minimum at x. Okay, G has a local minimum at x, but is that possible? Look at what we know about G prime x.
Less than.
G prime x is less than 0, and that is how we started with an observation. Okay, if a function is differentiable and if its derivative is not 0, then it cannot have a local maximum or a local minimum. Okay? So that means since we know that G prime is strictly less than 0, right? So it is not 0, so G cannot have a local minimum at x. Similarly, it cannot have a local minimum at y, because G prime y is strictly bigger than 0. Okay, right. So what does this mean? It means that this point Z must be an interior point. Okay, right. Okay, so let us say okay, since what is our argument? Since x and y, or let us say since G cannot have local minimum at x and y, we must have x strictly less than z and z strictly less than y. Okay, x strictly less than z, and so z is an interior point. Okay, what is more, what we know that G is differentiable throughout AB, so in particular at the point Z also, and it has a local minimum at Z. So what is the meaning of this? That G prime at Z must be 0. Okay, since G is differentiable at Z, and has a local minimum at Z, G prime at Z must be equal to 0. okay. But what is G prime of Z? G prime of Z is nothing but f prime of Z minus gamma, right. G prime of Z is nothing but f prime of Z, that is because this is equal to, that is f prime of Z minus gamma equal to 0, right, and that is what we wanted to show, right. That is, given any number gamma which lies between f prime x and f prime y, there exists Z between x and y such that f prime at Z is equal to gamma, right. Okay. Is clear? So we have shown that derivative of a function must satisfy this intermediate value property, is this clear, and as a corollary of this we will show that the derivative cannot have jump discontinuities. It can have discontinuities of the other type, but it cannot have jump discontinuities. But anyway, since the time is up, that we will take up tomorrow.